Yes, sir. Good morning to everybody. Myself, I'm Dr. G.P. Bhavani, Head of the Department of Chemistry. Respected guest, Dr.J.Sai Chandra, respected Secretary, Lalit Kumar O. Jain, respected Management, respected Principal, Dr. N. Sujata, dear colleagues, participants, and my dear friends, a very good morning to one and all present here. It's given me a great pleasure to welcome all. Our, our college, Sri Chandraprabhu Jain College, offer a wide variety of programs, both the online and offline, with the main goal of advancing the skills of knowledge globally. In addition to knowledge to our students, it is completely in a today's prosperous society. First of all, I wish to appreciate to us who interest in exploring the knowledge in a sessions of online sessions organized by the WeCan Institute, the International Virtual Seminar on Chemistry 2024. I welcome our special guest, Dr. J. Sai Chandra, a professor of chemistry, Chittoor University of College Engineering, Sultan Sangareddy District, Telangana. Thank you, sir. Please welcome, sir. Let us introduce our chief guest, Chandra, sir. Dr. J. Sai Chandra is a completed PhD in Acharya Nagarjuna University. He awarded the first grade in PhD and in MSc Chemistry, Organic Chemistry. He has a lot of international patents, mainly for the Canadian copyright and Germany for the process. He has a membership in lot of society and organizations. First one, the Indian Society of Technical Education, ISTE. And second one, the International Associate of Engineering. And third one, Asian Pacific Chemicals and Biological Environmental Engineering Society. It is a main. Next, he has a lot of administrative experience in a R&D lab. He has a journal of reviewer and membership in a lot of journals, mainly for the Journal of Engineering Research and Science, and second one for the ISSRA Journal of Multidisciplinary Bulletin, and global third one is it's a main Global Research and Developments Journal of Engineering. The fourth, World Journal of Pharmaceutical Research, and fourth one, DKIRF journals, and many more. He has a lot of teaching experience from 2010 onwards, more than 17 years of experience. He has a lot of national patents, more than 11. It's a very complicated to get the patents. He got more than 11 patents, friends. He has published more than 10 books for the various main subjects of chemistry, in industrial chemistry and the chemicals for kids, and study for valuable among the secondary school students, basic principles of inorganic, organic and physical chemistry, growth of characters of NLO compounds and various. He has an award received from the various research and academic institutes, one for the Young Scientist Award 2021 and other one for the main Best Researcher Award 2018 and third one for non-SAF Meritorious Fellowship Award 2010. He have conducted a lot of FTPs and participated a lot of FTPs in a modern innovation, technical science and technology basis. He has published more than 22 journals for the elsewhere scopes and main bulletins. And also he attended a conference and workshop in more than 58. Thank you, sir. Thank you for your cooperation. And thank you, sir. Please proceed, sir. May I hand it over the session to the chief guest, Sai Chandra, sir. Thank you, sir. Please proceed, sir.
Thank you, madam. Thank you very much.
Thank you,
Is it
sir.
audible? Is it audible? Right.
Yes, sir.
Yes. Good morning, all. Good morning, all. Thank you, Bhavani, madam, for giving me this opportunity, giving related to this polymers topic as for your uh, future approach. And I myself need to give this as the polymers. As today's day-to-day life, we can see each and everything which we are going to observe this one as a polymer. And for our day-to-day life, as the polymer is getting more increased, the pollution also getting more increased. So this on this polymers topic, which we are going to learn is how much we are going to get survival, that much effect it is going to get on for this atmosphere. So towards this, we can see the first one as this polymer, as we can observe this one as the two classification, which we can see the major thing as poly and merge, which we can see it as many end parts. So merge means parts in the sense we can also observe it as a monomer unit, which we can see it as a single designed one, which has a functional group which approaches with the number of molecules to form a big, huger molecule size. So which we can see it as poly, the number, and we can say it as many parts, which we can see the made up of linking together of large number of small molecules, which we are naming that one as the molecules as monomers, which we can see here are the monomer units, which combines to form a chain format. So this type of chain formats will be major thing as which has based on its the formation of the chain, it can be derived its strength of the nature. And one large molecule which is formed here, as it has the tensile strength will be there and stronger will be there as long it is the monomer units basis. And here upon this, we can see different types of monomers we can observe here for our day-to-day life. As we can see the best example as ethylene, and we can see this one ethylene as any polymer which can be has which has to be formed is derived as based on its unsaturated double bond, and this double bond always splits to form a single covalent bond. This covalent bond nature which always designs to form a polymeric chain. This is a basic theme of any structural design of a polymer. And we can see number of monomer units which we can observe to form a polymer. Here we can observe this one as ethylene as the major one, and second one propylene, vinyl chloride, tetrafluoroethylene, and isoprene units. We can observe this one as different monomer units which already has this unsaturated double bonds, and these functional groups can vary, which one we can see it as methyl group is there, chlorine group is a fluoride, different functional groups can vary, and this based on this unsaturated double bond it splits towards to form a chain format. And we can see number of other examples also here in this, and basically the basic example which you can see it as ethylene as a monomer unit. And here we can see that as how the mechanism it is going to happen here. And we can see it as the ethylene as the molecule, which we can name it as ethene or ethylene, any numerical format. We can see it as the molecular weight, which is designed here as that one 28. And this one on formation of a polymer, it designs to form a unsaturated double bond. It designs to form a single covalent bond nature, and this on formation it leads to the formation of this molecular weight approximately of 28,000. And based on this we can design this one as n number. We are naming here n number means it has number of infinite molecules, and n number always designs about the degree of polymerization. We can see it as how much strength, the tensile strength it has. We can design it based on the n number. And we can see second example as butadiene. We can see on polymerization it is going to happen and it forms a polybutadiene here we can observe as the degree of polymerization, which we are discussing now. N number. This N number always decides about the monomer units, how many monomer units are going to apply to form a polymer. And these polymers shows the strength of a each and every designed molecule. And based on that, we can see it as high degree of polymerization. It shows hard and heat resistant. And low degree
Sir, any signal issue, sir?
yes, some problem is arising here. Is it visible, sir, now?
Sir, visible, but it is in small size. Can you make it a full screen, sir?
Can it now, sir?
Yes, sir. Now it is visible completely.
No, go for the full screen option, sir. Yes, sir.
Yeah, okay. Sorry for the inconvenience, right? We can see here as the polymer which is going to form as the number of monomer units, which has placed here as the molecular weight 28 towards 28,000, which you can see here. And based on this, we are designing it as degree of polymerization here. And this degree of polymerization always designs about the strength of the nature of a polymer, which you can see here. High degree of polymerization is results to form a hard and heat resistant. And the low degree of polymerization, which leads to the soft and gummy nature. Sir, I think some disturbance here, right? Hello. Sir, hello.
Sir, yes, sir.
Yeah, some disturbance is getting some mute from other side.
Yeah.
Right. Based on this, we can see this one as the molecular weight of a monomer and as a monomer polymer, which we can see it as N equals to M by M. We can see it as M equals to NM1. It's N number of monomer units. So here we can see that N, which is placed here, which you can see it as the degree of polymerization, which you can see it as 1000 as its molecular weight, or, not, or we can see it as the strength of a particular polymer. And based on this, we can see different types of classifications are there. Here, coming to this classification, it designs based on the nature of activity of a polymer, which we can see it as first one on the basis of origin. Origin nature, which we can see it as it can be designed in natural format and also in synthetic format. So here we can see the natural format, which we can say it as it is occurred by the nature, which is formed automatically from the nature, and it is very much usable towards the further process. And here we ourselves are determining that synthetic polymer from a natural polymer, and we ourselves are converting such type of natural polymer ingredients towards to convert into synthetic polymer. And in the sense, we can here derive this one as on the basis of nature of monomer units, which we can see also as homo and heterosynthetic polymer, homo and heteropolymers. And here the homo, which always we can see it as the general theme of the homo polymer, as homo designs always as a similar, or which we can see it as same type of monomer units. And here we can observe this one as it forms a linear branch and cross-linked format. And heteropolymers also the format which forms the same thing, but it derives as the different types of monomer units. And we can see this one as based on the chemical nature also. And this chemical nature always designs about this organic and inorganic formats of a particular form, a particular polymer, which you can see it as the number of carbon molecules which are involved in unsaturated double bond to form a polymer as organic. And in the inorganic format, which you can see it as silicon and rubbers are the basic materials which are going to derive the chemical nature of a particular polymer. And here, coming to this, we can see the nomenclature of polymer. And here in this nomenclature, it can be derived as three formats, which you can see here as images, as which will be as similar, and which will be as linear, and also which can be also cross-linked or branch. Different types of formats are there here, and basing on this structural or nomenclature, we ourselves can see this one as which one is more strengthened. We can observe easier there as the more cross-linked, as we can observe this one as more strengthened towards this polymer unit. And here, homopolymer, which we can see the example as the monomers of similar format. Which we can see it as A as designed here as this example format, which we can see the strength, which we can see the linear format of a polymer. And copolymer, which you can see it as, or else copolymer is also other named as heteropolymer. And here, this one also designed is as different types of monomer units which splits to form a polymer. And here we can see the alternating and block polymers also. And based on this, a graft polymer, which also can be designed this one as a chain made from one type of monomer with branches of another type, which we can see as a similar linear format can be derived with different. You can see here example as A is a linear chain and B is the other linear chain which is linked towards this A chain, and it always forms this one as a graphical format, which you can see it as graft copolymer. Graft in the sense different types of monomer units attached towards a linear polymer, and it forms a copolymer. Copolymer in the sense we can say it as number of different monomer units. And next part we can see the measure as tacticity. The tacticity in this sense we can see any carbon ethylene, we can see it as it takes a hydrogen of 6. We can take it as without unsaturated double bond. If it is placed saturated bond, we can see it as hydrogen number can be get decreased, and based on that hydrogen or any type of functional group which is placed here, it will be as most linear format of a chain, and this designs the tacticity of a polymer. And we can see it as the basic orientation design of a monomeric units in a polymer which takes place in orderly or disorderly, any type of format which can see, as we are naming that one as Tacticity. When based on these orders and disorders, we can design this classification of Tacticity. As we can see, the first one major thing as isotactic. In this isotactic, we ourselves can design this one as a similar, which we can see it as head to tail configuration, as the functional groups are all on the same side of the main chain. We can see Fg, the functional group which we are indicating here as Y. And this Y are placed on the similar top side of the carbon atom. And we can see this type of format as isotactic nature. And here we can observe this one as syndotactic and also atactic condition. And syndotactic, in the sense we can see the functional groups occupy alternating positions, which we can see the position of Y, which we can place here. One is placed here down and the top and down, and we can see the next chain. If it continues, it repeats the alternate position of the Y functional group. And here we can see atactic type of polymers also, and which you can see the functional groups are arranged in random manner, which we can see the syndotactic and the atactic type of polymers can be designed in a similarity we can observe as alternate arrangement and also the random manner of arrangement. And we can see different types of examples. We can see atactic polypropylene is a gummy solid, while isotactic version, which we can see high crystalline and tough molecule. And based on this is the nature or origin of a different types of polymer classifications. And here we can see now we are going to study about the basic theme of a polymer based on the mechanical format. And here we can design this one as mechanism of a polymer, which is going to be an three types of mechanical format, as one is addition, condensation and copolymerization. And here we can observe this one as the condensation, copolymerization, addition. These three types based on the monomer units, which we have seen the previous examples of different types of monomer units. And these monomer units will be helpful towards to place that monomer to attach with number of similar or different monomers to form a copolymer or a homopolymer. And now we are going to see about this types of polymerization. And this one is in the sense of monomer units, which is going to form with example of basic, which we are going to see here as ethylene. As we previously discussed, as this at high pressure and pressure of oxygen, catalyst and everything else, it is going to form some polyethylene, which we consider as from ethane compounds towards polyethylene or polyethylene or poly, you can see it as molecule which is going to be based on the monomer unit. And here we can see with the based on the mechanism format, which you can see this as different types of monomer units as examples. We can observe here one is ethylene, next propylene, next styrene, vinyl chloride, tetrafluoroethylene. These are the different types of monomer units which are going to form on polymerization process to form polyethylene, polypropylene, polystyrene, polyvinyl chloride and also polytetrafluoroethylene. You can see different types of monomer units. Based on this, the functional group which is arranged on the monomer unit of a particular carbon atom, this polymer can be designed. And here we can see the other examples also, formation of the polymers with polyfunctional monomers, which we can see that like water, HCl, etc. Examples we can see the nylon 66 also. And these are some monomers towards the formation of polyesters and some amides, which we can see it as the monomer units which are formed towards the polymer. And some adipic acid on combination with 1,6-diaminohexane nylon 6 which is going to form this one. And these are some different examples which we can observe for the formation of a polymer unit. And this one is the monomers of to form a polymer as isoprene as the we can see this to form a polyisoprene, which we can see isoprene is the basic structure of a natural rubber format. So this rubber format is always designed to form a polyisoprene, which natural rubber to form a polyisoprene. And also we can see beta D glucose, amino acids and some nucleotides, etc. We can see based on this number of additional format of monomer units, it is going to form different types of polymers. We can see this one monomers as one of the chemicals which you can observe, and also some amino acids, nucleic acids, and different types of monomers we can observe to form a polymer. And these are some specific type of addition polymerization, which you can see the butadiene on combination with styrene to form as we can see the SBR styrene and butadiene rubber polymer, which we can see on combination of this two different monomer units on combination to form a strong format of styrene butadiene rubber, which we are also naming this one as Buna S, butadiene, and also the styrene. B stands for, we can see butadiene, and also this one S stands for the styrene, which we can name this one as styrene rubber or styrene butadiene rubber. And in this, coming to this mechanical format, it always designed show that as three-step mechanism, which we can see it as one is initiation, second one will be propagation, third one will be termination. These are the three-step mechanism which always shows that as a mechanical format from a monomer unit towards a polymer format. And here in this monomer unit, we can see it as an initiator will be there. And initiator which always designs to form a polymer. I mean, which we can see it as, which can form as, we can see, which can form as a radical format, which can form its ionic format, or which can form its one as condensation polymers. And based on the initiator, which we can design this as a polymer format mechanism. And here in this example, we can see here as initiation of for the formation of free radical mechanism of a addition polymer. And in this, we are taking the initiator as hydrogen peroxide, H2O2, which we can name this one as structurally. And in this H2O2, always on heating, it going to form some 2OH dot. We can see it as 2OH free radical. I mean, two molecules of OH radicals are going to form as free electron design format. And this free radical which is placed here is going to attach with the monomer unit, which we are going to add for the furtherly process. You can see here we are taking this one monomer unit as ethylene as one of the basic compound which we are monomer unit which we are taking it as, and we can see a number other monomer units also based on the your formation of the polymer, which you can see take vinyl chloride, styrene, as different formats of monomers can be attached towards this free radical, and it is going to form some, you can see here as free radical monomer, which we can see it as the monomer which is attached towards this free radical to form a monomer free radical, which we can see the radical will be repeated here, and the unsaturated double bond it splits to form a covalent bond, and which is attached towards this to form a bonding of O and carbon, and we can see here as the formation of monomer free radical. And this is a primary initiator step for the formation of a monomer free radical. And in this second step, we are going to for the second step as propagation. And this propagation step always designs about the continuation of a polymer formation, which we can see it as a living polymer can be formed, or else we can see observe this one based on the number of monomer units we can attach towards this propagation step. And in the second step, basically we can see here as the initiator which is done in the first step will be attached towards a monomer to form a free radical monomer. And in the second step, the monomer free radical is furtherly go on for the addition of other monomer unit, which we are naming, which we are taking it as a similar monomer, which is from the first step, as other monomer can be attached towards this. Example, we are taking it as here as ethylene. Ethylene is again attached to this monomer free radical. On further addition, it is going to form some living polymer, it is going to be obtained. And this is the middle step for the formation of a polymer. And next will be the termination step. And in this also the second step propagation, we can see the radical format. And in the termination step, which we can see here as the two types of living polymer, free radical polymer, which is going to be attached with each other and to form a terminated step of the polymer. And here this complete dead polymer can be obtained here in the termination step. And in this, the complete formation of monomer units attachment and also the formation of the polymers is completed with this three-step mechanism of this polymerization process. And then this is the basic step for the free radical addition polymerization. And in this, we can also see as degree of polymerization, and also this, which always shows the crystalline regions with amorphous, and also we can see the all molecules which are arranged in an orderly manner, and also we can see the degree of polymerization. And based on the monomer units, its high density, sharp melting point, strong or brittle or hard, which is mechanics. We can see that based on the monomer unit which is attached here. And this amorphous polymers always possess the melting points and also the softening points of a particular polymer. And this we can see here as the melting and gas transition temperatures, which we can observe this one as the lowest temperature beyond which polymer becomes hard, brittle, glass-like, or temperature which polymer experiences transition from rubbery to rigid states, which we can then naming this one as glass transition temperature, which we can design this and we can note this one as the labeling DG. And this one always indicates the brittle nature or the strength nature of a particular polymer. In this state, we can see the solid tends to shatter if it is heat, or since the molecular chains cannot move easily based on the monomer units. And this temperature above which the polymer turns out into flexible and elastic and also the rubbery. Based on this, we can design this one as the TM mechanism. And here we can see this structural design to form as hard brittle towards, we can see the polymer, it converts to hard brittle shape and also towards this fluid mechanism shape, and which we can see this based on the increasing or decreasing of a particular temperature. And also here we can observe this one as beyond the glass transition temperature crystalline amorphous polymer which behaves at differently as shown in the diagram, as we can see here as crystalline nature towards viscoelastic and towards the liquid metal, and also different types of format based on the polymer format. We can see the crystalline nature designs to form viscoelastic and also finally to liquid melt viscofluid state. And also next big step we can see the amorphous state of the polymers, which is powdery substance, is rigid hard brittle like glass material, which is formed towards converts towards rubbery soft and also towards liquid. And based on this increasing temperature and decreasing temperature, this effect of polymer can be designed. And next is TG and TM, which shows it as the significant parameters, which always indicate the temperature regions, which are discussed now as increasing and decreasing of the temperatures. And these are some factors related to this TG. And this one, average molecular weight calculation. Here we can see this as the polymer sample, which is N1, N2, N3, different types of, because you can see the number of molecules with molecular weights M1, M2, M3, which you can see on structural design of the formula. We can see it as how we are going to calculate the molecular mass of a polymer. And these are some different calculated molecular formats we can see here, which you can see mass of each molecule M1 and N1, M1. You can see it has the different types of calculated formats of different types of molecules. It's the average molecular weight calculation. So these all which we can see as for the calculation of the strength of a particular polymer, which you can see. And this is the next topic you can see here as rubber. And now till now we have observed some polymeric classifications. And polymeric classifications always shows as it one based on the monomer unit. As we can see, ethylene, vinyl chloride, styrene as different examples, etc., based on the monomer units attached towards a initiator to form a final terminated polymer. And now we are going to see that as rubber. Rubber is a basic material who the Hermann Schrödinger formulated this macromolecular structure, which we can see as the Nobel Prize winner. And based on this, he himself shows it one as isoprene units, always designs to form a multiple nature of a formation of rubber. The isoprene unit, which you can see natural rubber, is pure white in color, as we can see it as milk. And this white rubber is always converts to the simple mechanism of synthetic nature of human equipmental organized themes, which can convert those rubber into different colored formats. We can see in different examples also. And in this, the polymers or the elastomers are rubbers, which you can see the processing elastic nature of extent up to nearly 200 to 300%, which we are naming this one as elastomers. The elasticity nature which is present towards this rubbers to show as 200 to 300%, which are named this one as rubber material. And amorphous polymer with numerous cross linkages or high degree of density is always shows it as deformed stretching and regain of original format. When stretching force is removed, it gets towards its original state of nature. And this one we can see it as the excess rubber, stressed rubber, and also back to original position rubber, which you can see here as this liquid format, as we can see here. And these properties, we can see any type of material which has this properties, as we can see as the flexibility, tensile strength, impermeability to water, and high resistance to abrasion. So there are the different types of properties towards rubber material. Due to these properties, rubber is highly useful for industrial as well as the domestic purpose. Nowadays, we can see rubbery material are very, very much essential towards the further process in the day-to-day life. And here we can see the rubbers, which you can see types. And what are the types of rubbers? We can see as the polymers which we have seen earlier, as one is natural and synthetic, as in the sense also, as in the sense also we can observe here as types of rubber. And in this rubber material as natural and synthetic, the same we can observe here. One is obtained from the natural source and second is from man-made or synthetically, which we cannot see it as. And the natural rubber, which you can see the image on the right side as heavier resistance as the major basic material of a rubber, which is tapped every second day for its sap and known as we are named as latex. By making slanting cuts in the bark of the tree, which we can see here as the milk of rubber tree, as which is cut down and the drop by drop material can be placed on the bucket or the vessel which is placed here, which is majorly part to get stuck up with the rubbery material. And these are the major inputs or the raw material of a rubber. This raw material we are naming it as latex. And this latex is collected and acetic acid is added to it, and so it is precipitated out to the rubber and then hardens and coagulates to form a hardened material. And this on further synthetic format which we can get towards to conversion into the other format of the rubber. And we can also observe here as being washed and dried rubber, it is cured, and especially smoke houses to protect it against microbial attack. And also pureed and rubber format which are delivered and companies towards the worldwide. And this we can see the natural rubber we can observe majorly from our southern region as the Kerala and different parts of area. We can observe this most of the generating natural rubber, and from this itself the complete transportation is throughout the worldwide is going to be happen. And this one natural rubber which we are saying it as a latex, and this one latex we are naming this one as a polymer of monomer unit isoprene, which we are getting it as 2 methyl 1 comma 3 butadiene. And this is a basic structure which shows the tensile low and also elastic over the narrow range of temperature. And this on further process of this isoprene, it is going to helpful for the future rubber material of, we can see it as rubber as nylon 66 or burians. Like this we can see as thiocols, as different types of rubbery materials can be obtained based on its tensile strength. As the polymers which are discussed earlier, these rubbery materials also can be formed based on its tensile strength. And this rubber, which is composed of all cis-linked isoprene units, which forms an amorphous structure that is highly elastic. On the other hand, we can see the gutta percha, and which is polyisoprene compound made of all trans-linked isoprene units, and this forms a linear strands which can interact into crystalline arrays that have plastic properties and also as non-plastic materials. Based on this, we can see different types of formats of rubbers, isoprene units to form a polymeric rubber. And this one is amorphous structure of a rubber, and we were naming this one also as gutta-percha forms of the crystalline arrays. And it's, we can see the plasticity nature each and every material of the polymer or rubber or any type of, which can be biodegradable, any type of polymer, it has its plasticity nature, and this is greater than the elasticity, and it can sustain the stress, and when stretched to a great extent it undergoes some deformation permanently, and also has large water absorption tendency with its weaker period. And this one is the major limitations of natural rubber is, we can see it softens at high temperature and becomes brittle at low temperature. We can see, I mean, as it can get strength as at lower temperature, and it gets softer. It can be converted to other state of format at high temperatures only. As we can see the plastic materials also, we can see on high temperature the plastic hardened material which is converted to a liquid format, and it can be as lower temperature it gets harder. And this natural rubber which is attacked by acids, oxidizing agents or non-polar solvents oxidized by air, which is converted to form a vulcanized rubber. This vulcanized rubber is a term, we can name this one as a synthetic rubber, and this natural rubber we are naming it as latex or isoprene units, and these both of these to convert to form synthetic rubber. And this vulcanization process is completely essential compounding rubber with different chemicals. We can see it as addition of these different rubbers, different materials as some sulfur, H2S, benzoyl chloride or acids, any type of, we can see for conversion of this softened material towards hardened material on increasing the temperature. The heating of this raw rubber with sulfur at 100 to 140 degrees centigrade, and we can see the sulfur enters the double bonds, rubbers, and forms cross linkages. We can see it as carbon to carbon. We can see in the middle of these two carbons, we can observe this cross link as sulfur can be entered. As the linkage between the two carbon, we can observe this as two sulfur bonding. Sorry. And this brings the stiffening of the rubber and also anchoring of restricting internal treatment of these cross linkages. So these cross linkages of sulfur which is attached are benzyl chlorides or anything else which are chemicals we are adding towards this natural rubber. It makes this natural rubber to get more strength here in between these two carbon atoms. These two carbon atoms, when the attachment of these chemicals are mediated or attached in between these two carbon atoms, that rubber will be more strength here. And this one, we are naming this one as a vulcanized format. Here, in this structural design, we can observe here as on complete vulcanization, we can observe this one as here, the sulfur we can see in between of these two carbons, and the here also we can observe here. And at a temperature of 110 to 140 degrees centigrade. And this temperature variation always shows it as the complete linkage of the sulfur into the carbon chain format. And this sulfur in between of these two carbons, which we can see it as, they gets more strength here. If it is not inserted in between these two carbon atoms, the particular chain is more and more weaker. And based upon this addition at 140 degrees centigrade, the sulfur, when it is attached towards this, it melts to form a vulcanized format of rubber, and it is more strengthier than that of the previous linear linkages. And we can see here, based on this, the toughness or stiffness of vulcanization depends on the amount of sulfur included. What I'm saying it now is a previous also. Based on the sulfur content which is attached towards this at 140 degrees centigrade, this bondage which is formed between the two carbon atoms, which shows it as the toughness and stiffness of a particular chain. And this is flexible tied rubber, and also sulfur content is from 3 to 5%, whereas a tougher variety, ebonite content of sulfur is 32%. And this ebonite is so tough that it can be machined and has very good electrical insulation property. And we can see insulation in the terms, we can see good resistance. I mean, good, you can see it as for the electrical formats. And these are some different raw rubbers and vulcanized rubbers, and based on its strength, the chemical resistance, durability, propertical nature of a rubber material. We can see as elasticity for the raw rubber, it is very high, and vulcanized rubber, that means we can see the two classifications, as this one is raw, is the natural format, and this is a synthetic format. We can see the two classifications between these two properties are based on the natural properties of this rubber. And second is tensile strength, and this tensile strength is for the natural rubber is 200 kg per centimeter square, and we can see it as for the vulcanized rubber 2000 kg per centimeter square. And also the chemical resistance, it's very poor, but it is higher, and the durability is very less, and in the natural rubber, and the durability of vulcanized rubber is very high. Durability in the sense we can see it as lifetime of this rubbers, and the quality is raw rubber inherent and can be controlled by vulcanization based on the chemical which is going to be attached or which is going to be added. And here we can see the some applications of rubbers, as we can observe this one as rubbery materials which are remarkable resistance to electricity, and we now we're going to discuss now, and is used as insulating coating on wires, cables, and used as electrical power transmission. Insulator wires, which is covers the copper wire, and it protects the from the human usage, and it also used for the resistance. And due to this elasticity, it is used for fabricate rubber hands, and also this rubber boots, golf balls, etc., different tubes of automobiles, everything else, which in not even we can see nowadays, which can be made for different types of designs, and foam rubber, which is used for making pillows, cushions, mattress, automotive pads. Now we can see different types of cushions are also being made nowadays, which with different types of formats. We can say foam beds. We can see observe nowadays, and we can see the polysulfide rubbers, which we can see the solid propellant fuels for rocket motors. And these are some, till now we have observed this, some mechanisms of how we are going to be utilize these rubbers. And now we can see this as rubbers preparation. Now vulcanized rubber is prepared by the addition of this sulfate. And we can see this synthetic rubbers, which are how it is going to be prepared. We can see the basic example as vinylized rubber, which we can see it as butadiene and styrene combination. We can see here at the reaction as butadiene on reaction with the styrene or copolymerization, which we can observe this one as SBR, which we can test styrene butadiene rubber. And next one we can see ethylene glycol on polymerization. You can see it as ethylene diisocyanate on polymerization process. It is going to form polyurethane rubber. So these are different examples which you can see it as for the formation and the preparation of rubbers. And these are some industrial polymers, which you can see it as based on this world consumption of the synthetic polymers, 150 million metric tons per year has been generated, which you can see plastics of 56%, fibers of 18%, synthetic rubber of 11%, coating and adhesives of 15%. So based on these percentages, which you can observe as the synthetic rubber is going to be developed in 11% to 12, 15, 16, etc. It is going to be increased based on the natural rubber material which you are getting. And the coating and adhesives also, the coloring agents, which are nowadays getting increased more and more as the synthetic polymers, which are going to be increased, the plastic materials and also simultaneously fibers. Also, the majority of the part here we can observe based on these four categories. Plastic material has the first ranked material, and it is going to be generated. It is generating and generating, and it is the number of generating materials which is we can see it as the plastic is the first thing, and which is majorly and destructed material. I mean, most advanced or most time period which is taken to destruct that material is also the plastic material. But nowadays it is going to be as is getting converted to lesser carbon moderated molecules, and also these plastic materials can be destructed or towards this further usage to avoid such type of natural disasters. We can see here as also plastics, which you can see two types of classifications, thermoplastics and thermosettings, which you can see that some polymers when heated, it becomes soft and can be molded into shape, which we can see example as PVC, polyethylene, nylon, we can see the sealing wax, different types of materials. We can observe this one as example for thermoplastics. And the thermosettings, we can see it as bacalline and polyester materials. And we can see on heating, polymers undergo chemical change and become an infusible mass, which cannot be reshaped again. And this is the major difference between the thermoplastics and also the thermosettings. These two differences, we can observe this one. Thermoplastics, PVC is the major material, polyethylene is the basic material, and which can be converted to, it can be molded easily based on the molding techniques. We can see different types of molding techniques nowadays are there for preparation of any bottle, any glassware, any type of material, plastic material, rubbery material, which is going to be which is going to be prepared. It has some molding techniques, which can see the injection molding like this. We can observe as blowing molding. Different types of formats are there for the preparation of different materials. And these are the major differences between the thermoplastic and thermosettings of polymers or soft on heating, which are already discussed here, and can't be reshaped, recycled, and cannot be reshaped and recycled. Thermosetting and thermoplastic, some variations, and with some examples we have mentioned here: polyethylene, polystyrene, and nylon 66. And here, this is unusual affinity of high polymeric materials or articles, which you can see. So it consists of high polymers and also this additive nature. And the main compounding ingredients, which are we can see here, resins, which are binders, which we can observe this one as holds different constituents, additives together for natural synthetic resins, which are used in this case. And next one is the plasticizers, and which has this low molecular weight organic liquids which are added to polymer and improves the flexibility. Added, which is 8 to 10% of the total bulk of plastics, oils, camphor, diethyl phthalates, which you can see small molecules of which penetrate into the polymer matrix and neutralize a part of intermolecular forces for attraction between macromolecules. For the formation of huger size of macromolecules, these plasticizers are included. And these plastics may be variant based on the material which you are going to use. Sorry. And these are some stabilizers, fillers, lubricants. All these materials are included for the formation of particular design format of a bottle or structure design, anything else which you can see. All this has to be included for the preparation of particular material. Stabilizers. Sorry. Stabilizers, the most polymers which do not possess chemical stability. And preparation of this bottle which is prepared, which has to be get stabilized or format, but it has to be fixed for the particular format. And this type of fillers or extenders also been there, and also some lubricants has to be attached, and some catalyst, coloring materials. There's some different ingredients to be prepared for the additional attachments for the preparation of material. And these are some preparations of materials of the polymers you can see here. Sorry. This is a phenol formaldehyde resin, and which gets prepared, and 4-hydroxyl alcohol help. You can see hydroxybenzyl alcohol. And polymerization process, it is going to form this one. Phenol and formaldehyde, both of these combination to form a phenol formaldehyde resin. And this is a polymethyl methacrylate, PMMA, which you can see it as for the preparation. And methyl macrolide on preparation of the free radical vinyl polymerization is going to form methyl macrolide.
சார் என்ன சொன்னாரு? என்ன சொல்றாரு சார்? Hello, sir.
Yeah, yes, ma'am. Yes, ma'am.
It's completed, sir.
Yes, 1 minute, madam. It's completed. Almost to the end. And this is a PMMA, is a transparent thermoplastic which offers for the preparation of this polymethyl methacrylate. These are the properties and applications. And this is also one other format of this preparation, ureoformaldehyde resin. And they are the conducting polymers, which you are going to see it as the poor conductors. And some the doping techniques, which you can see as the time is lesser, you can skipping this. And there are some applications related to that. Okay, thank you.
Yes, sir. Thank you, sir. Someone asking questions, sir. Sir, may I proceed?
Yes, ma'am.
Yes, sir. One of the students from third BSc chemistry asking, what is the difference between the isotactic and the syndiotactic compounds, sir?
Yeah, isotactic in the sense we can see here as a functional group which is present on the carbon atom is similar. Yeah, whereas the syntotactic is, which is isotactic, is placed on the topper side or the bottom side, which can see as, and syntotactic is getting alternate arrangement. This is the difference between these two.
Okay, sir. Same questioner. What is M and M not in a degree of polymer?
Yeah, M in the sense we can see it as a monomer, and we can see it as a monomer unit, and also the MO it descends about the polymer material.
Here it's only for BSc students, that's why you're asking some questions, sir. Sir, other one is, what is difference between the same question? What is this? So why vulcanization process take place in polymer?
Yes, vulcanization process is particularly essential towards the strengthening of the material. Yes.
Okay. Other one is what is the orientation of amorphous polymers and semi-crystalline polymers?
Amorphous in the sense of powdery material, and semicrystalline is also this next stage of this amorphous, which we can see it as.
Yes, sir. Thank you very much, sir. I hand it over the session to the vote of thanks. Miss Maithili ma'am, Assistant Professor, Department of Chemistry.
Yeah.
Ma'am, please proceed, ma'am. Good afternoon to all. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. Let me first of all start by giving glory to the Almighty God for making today's section a resounding success. First and foremost, I thank our special guest, Dr.J.Sai Chandra, for sharing our talent and important work with us. Together, we have provided us with invaluable information regarding polymer chemistry. With a great pleasure, I would want to express my gratitude to our management for providing this opportunity and for agreeing to host this webinar. My heartfelt thanks to our esteemed principal in charge, Dr. N. Sujata, is the driving force behind the encouragement and strong belief in teamwork. I consequently put into my HOD, Dr. G.P. Bhavani, and the entire team, the participants, and my lovely students to express my gratitude. I thank our program manager and CRO, Mr. Balaji sir. Finally, I leave you this inspiring quote by Martin Luther King: "An individual has not started living until he rises above the conceit of his individualistic come to the border, concern of the all humanity." Once again, I thank you all for your attention. Thank you. Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you, sir. Thank you very much, sir. Bala, sir, thank you very much, sir. Please.
Thank you, madam.
Yes, sir. Thank you.